United in AI, we learn and lead, ensuring we always stay ahead. February 2022, Russia launched a full-scale invasion of Ukraine. To support the Ukrainian tech sector, the largest AI community in Ukraine, AI House, brought together global AI experts for a charitable education project, AI for Ukraine, lectures and workshops about the latest in AI and ML in exchange for donations to Ukrainian defenders. This time, AI House teams up with one of the most powerful Ukrainian AI ML tech companies, Rush, for AI for Ukraine Season 2, to assist Ukrainian AI talents in expanding their network, equipping them with the most current and relevant knowledge in AI and ML, and raising funds to support Ukraine. Join AI for Ukraine Season 2. Harness the opportunity to learn, network, donate, and support Ukraine.
Hi everyone, and welcome to the first lecture of the second season of AI for Ukraine project. My name is Bogdan. I'm gonna be the moderator of this session, and I am Chief AI Officer of the company Gathers. So to start, let me share with you about the project. AI for Ukraine is the charitable initiative created by AI House, which is the largest artificial intelligence community in Ukraine that was launched in 2022, right after Russia launched their full-scale invasion of Ukraine in February. The purpose of the project is to provide Ukrainian AI enthusiasts with access to the most current knowledge, to encourage collaboration, share experience with international community, and raise funds to support Ukraine defenders. Now, AI House and Rush, one of the most powerful AI/ML tech companies, we are gathering for the second season of this initiative. All lectures will be available for further review after live translation, so be patient, and it's okay if you miss something during this live session. And let me remind you that it's extremely important to keep donating and supporting Ukraine. So please take a moment to donate by scanning the QR code or using the link in the description. And all of the funds will be immediately sent to the charitable organization Reactive Posts and will go to the needs of Ukrainian defenders. And the speaker of today's lecture is Lukasz Kaiser, who is the top AI expert and member of the technical staff at OpenAI. The topic of the lecture is going to be Deep Learning Decade and GPT-4. Today, we will discuss the research that led to the creation of GPT-4 and ChatGPT, and also we'll explore the evolution of transformers and discuss what future holds for AI industry. And we have the question and answer session after the lecture, so don't hesitate to write down all of the questions to the chat below. And before we dive into the lecture, let's get to know each other a bit. So please share in the comments where you are listening to us from. While you're writing, I'll get Lukasz to join us.
Can you hear me? Hi.
Yeah, hi Lukasz, it's a pleasure hearing you.
Hello. Good to meet you. Thank you for the invitation.
Yeah, thank you for coming. And just to get us started, one question that I personally want to get to know from you is, how often do you personally use ChatGPT?
I use it every day.
Yeah.
Yeah,
And
it's very convenient to search for things, and I do a lot. Recently, I do a lot of picture drawings because it works with DALL-E, and it's a lot of fun to watch it.
And is it only ChatGPT, or do you have like other tools that are in your daily routine that you use?
Well, it's mostly Emacs.
Yeah.
And Google, of course, and Slides and Docs and Slack. We use Slack at OpenAI. So yes, there's a lot of tools, but chat is like the only like AI tool. Even though AI is everywhere now. But
oh yeah. Okay, so let me take this moment to pass the microphone fully to you. Like, the stage is yours, and let's get started. And I'm really excited about this session today, as I'm sure all of our listeners.
Thank you very much. And as Bogdan said, don't hesitate to ask questions. We leave some time at the end to answer them. Thank you very much. So I want to talk about, I came into deep learning about 10 years ago. Before that, I was doing more of a theory of computer science. So these slides are a bit about my journey, but it coincided very well with what was happening in deep learning in general. So I want to show you that in these 10 years that passed, deep learning has changed very, very much. And I think this is important to know, because people very much focus on what is right now. Like right now, there is ChatGPT and large language models. But if you try to build something, if you're making something new, it will take some time to do it. For example, 2 years. And in 2 years, deep learning will be somewhere else. Every 2 years, deep learning has been in a new place. So it's very good to think where deep learning will be, because whatever you're doing right now will actually come to fruition only some years from now. And this will be a different world. This will not be the world of ChatGPT anymore. So this is a story of how things were changing. Of course, nobody knows what will happen in the future, but if you think about how things were progressing, you can start thinking about where they will go later. So when I started, I joined Google in 2013 and started doing deep learning for parsing. I actually started on the parser team that was not using deep learning, and then moved to use deep learning with it. And at that time, the whole job was to just show that you can use deep learning for anything. People just did not believe that deep learning can be as good as systems that were written specifically for something. So we were writing parsers, and people would believe that having a handwritten parser is better than having a deep learning parser. People believed that if you want to do machine translation, like in Google Translate, then you should use a specific machine translation technology and not use like some generic deep learning thing. So the first years, it was very important to just convince people that you can take a neural network, train it with data, and that it will do as well or better than these specific things that already existed. And that was quite hard, but it worked. And so that these were the first years. And so then people were like, okay, it works, but can we make it better? So this was the years of new architectures, like transformers. It all became better because now there was interest in pushing a lot into better neural networks. Then came the realization that neural networks needed data. It was like training for translation, training for parsing, for sentiment recognition. Every single task had its data set, and you would train on that. So later came this realization that, well, you can actually just train on all of the internet. This is called self-supervised pre-training. You predict the next word, you train on a huge data set like all text of the internet, and this network works much, much better. But it needs to be a big network. So after that came the realization that, if you make the networks bigger, you can actually very predictably see how much better it will get. So that led to GPT-3. That led to some of the networks that were already showing like these wonderful capabilities that we have now. And then the recent years were like, okay, so we have these very capable models like GPT-3, GPT-4 was training, but can we make them actually like just do something for you? And there is where reinforcement learning with human feedback and like the expert data came in, and that led to ChatGPT, and now we have this with GPT-4. And then, so where will this go? Where will this continue? I will come to this more towards the end. So let's start with the early years, 2014, 15. So if try to move yourself to these years, I will give you the example of parsing because I worked on the parser team at Google. So nobody on the parser team wanted to do neural networks. Parsing was done with probabilistic grammars. You maybe learn a little bit of probabilities of the rules of your grammar, but it's a very complicated code that has a little bit of machine learning component, but not deep learning. And your task is to make this code better, not to like change it, because nobody believes that you can take a simple neural network and make it do these things that this very complicated systems that people have spent a lot of years building is doing right now. So the paper that kind of inspired in natural language the idea that maybe you can do this with neural networks was this sequence-to-sequence learning with neural networks paper by Ilya, Oriol, and Kwok, where they showed for the first time that you can take an RNN and train it on a lot of translation data, and it actually translates almost as good as a very handwritten system that translates English to German. And that was already big because people were like, well, how comes that this very generic neural network, an RNN, just trained on a fair bit of data, is so good? So that was quite shocking. And these were, at that time, these were RNNs. So RNNs are neural networks that process, they have an input vector, say a character in Chinese, a state vector, and they very sequentially process it one-to-one. And then when they decode, they process the output. This had an animation, but it doesn't seem to show for me, at least. So whatever. So that's how RNNs worked, and this paper showed, okay, RNNs can learn to translate almost as good as these handwritten systems. So my first paper in machine learning was grammar as a foreign language, where we said, well, if they can learn to translate, they should be able to learn to parse English sentences too. In the end, it should generally be harder to translate to a foreign language than to make a parse tree. And so the whole contribution of this paper was to say, well, since this network takes as an input a sequence of tokens and outputs a sequence of tokens, so if we want to create a tree, then you can just output a tree like written with brackets, and our brackets, they also were saying what they're opening and closing. So this is an example of a parsing tree, and you can generate the parsing tree with the network that just outputs brackets. And people were saying, well, this can't be right. This network doesn't even guarantee that the thing will be well bracketed. It may output something that has just weird brackets and is not even a proper tree. So why would you use such a generic network that can output anything to do this very specific task? And this is something that you'll see in AI all through these years, that people had a very strong belief that a system that's specific for one purpose, that does parsing, that does translation, that does image recognition, people had a firm belief that specific systems must be better than these general systems, well, because you're putting effort to make this specific system better. And I think the true deep learning, the true AI, starts when this flips. So now we know that you can have a generic system that's trained to do everything, and in particular, it's also better at doing some other things like parsing. So at that time, we did an RNN that was trained for parsing only, but it was a much more general network than the techniques before. And it turned out that if you create special data for it, it indeed can outperform the previous best parsers. So that was a big success. This cemented our belief that neural networks indeed can go very far and do quite amazing things. And as the years progressed, we later worked on machine translation with Google Translate, and indeed the translation turned out to be better than the previous handwritten systems, even with RNNs. And as the years progressed, there was later interest in making these things even better, since it was clear they can work. So the first translation results, so this was the first neural network that was used in production by Google Translate. And so PBMT is phrase-based machine translation. It's the previous system, the Google Translate before 2015. And it had these are scores where humans give a score where 1 is the lowest and 6 is the best. So you see, like, English to Spanish was already not bad, 4.8 on average. English to French was even better. But for example, Chinese to English was really not great. And GNMT is this first RNN that translated that has replaced the phrase-based system, and it gave improvements over the board that covered, like, it was more than half of the distance to what human translators get scored. So that was a big argument for the translation team that this is something really good. Like, it can bridge over half of the gap to human translators. But could we do better? These RNNs, they were quite slow. They could only do one sentence at a time. They were very sequential. So it was not a great fit for the GPUs and TPUs that were being built at the time. And that's how we came up with this architecture called the transformer, which also had an animation on the left side, but I mean, I can't see it. So the transformer is a network that is not recurrent. It doesn't do any, at least during training, it doesn't do any of these sequential processing of one vector that gets passed and passed and passed. What it does instead is it takes the ground truth, and every token that is in the future can attend to all tokens in the past. And what does it mean to attend? Well, it's a simple mathematical operation where vectors seek vectors that are similar to them by dot product. And then there is a softmax that selects the most similar ones, and you get the values of these vectors transferred to you. So it's a way to access information in the past and to bring it to you by similarity rather than by this recurrent mechanism that the RNNs have. And this is extremely parallel. And it turned out that it tends to generalize much better than anything that was before. So blue scores are a way to measure the quality of a translation system. It's like an n-gram metric comparing to the golden translation by a translator. And you can see, like, the blue scores of the early networks on the English-German, which is so the blue scores, you can only look for them for a specific language. So they were around 23, then they improved to 24, 25. You could ensemble, like, very big networks, you maybe get to 26. And the very base transformer was immediately 27. So that was quite surprising to us. If you took a bigger transformer, it was 28. And if you trained it a little better, it was 29. Human translators are about 31. So after 30, these scores, they lose meaning a little bit. So like, the goal was to get to 30, and it almost got there. So we were very impressed by that. And on the other hand, transformers were also much faster because they were doing everything in parallel. So they were running much faster on GPUs and TPUs. And also they have, they simply need also less computation to get to the same result. So this was in these next 2 years when we started, we knew neural networks can do it. We started optimizing them, and the transformers came out, and they could do things really well. Like the gap to the human translators were almost fully bridged. That was a great result, and we were very happy about it. So what came next? Well, later people were like, okay, so we have these very good networks, but we train them for every task separately. There is the translation to this language, to that language. Could we just train them? What would that even mean? So there were two networks that did this. The first one was GPT-4. Language models are unsupervised multitask learners. And the other one was BERT. Both of them were transformers, but one was a decoder. So one was learning to predict the next word, like GPT still does. And the other was an encoder, meaning it was randomly removing some words, say 15% of the words, and was learning to predict all of them from the whole context, the future and the past, and in this way building a representation. But what both of these things had in common is that they trained on basically whatever text you could find on the internet. So while they were different sides of the transformer, one was a decoder, one was an encoder, I think the big step that both of these papers made was like, don't train for any specific task. Pre-train on a large corpus, and then later you can use this model, maybe you'll tune it or use it in whatever. And what happened in between is like, you can pre-train on text, but you can also pre-train on text and images. And that was the first DALL-E. DALL-E predicts an image by doing like a patch of pixels, one after the other, pixel, 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 pixel. The image is a sequence for this model. So it has a text and it needs to generate an image. And as you can see, it has learned not just to regenerate images that were in the training set, but it has clearly learned to modify concepts that are in the image, because you cannot find a baby daikon radish in a tutu walking a dog on the internet. It wasn't there until DALL-E. The prompt was chosen specifically to check if the model can do something that it's never seen before, and you can see it can. And another prompt like this was an avocado chair. What is an armchair in the shape of avocado? Who knows? Well, these are the ideas from the model of how it can look. So it started to be clear that these models, given just their pre-training on the internet, can learn to generate things that they haven't seen before, that go beyond their training data. GPT-4 was a model just trained to predict the next word on a lot of data from the internet, was good enough to start like being interviewed in The Economist. It could like generate like 2-3 sentences that were reasonable. So the human asked a question and it would generate a reasonably sounding answer. And so that was the years of pre-training, right? It was found out, oh, okay, so we can now just train on all of the text or images of the internet, and that will be good. But the idea was like, okay, you can train bigger models, but will that help? So the next question was, okay, should we just train a bigger model? But how? Like, will it be? It will be better, but will it be much better? A little better? How much better should it be? And that's where the scaling clause came. And I believe the scaling clause were one of the biggest steps that allowed what we have now, which is training really big models, because and that the paper was scaling clause for neural language models, because without the scaling clause, like, you train a bigger model, it will be a little better, but how good should it be? You don't know. And that's what the scaling law tells you. So if you train models of different sizes, so every blue curve on this picture is one training run of a model, and the x-axis is the model size or how much compute you put in the model. And to make this work, you need to have a recipe. So if you make a model bigger, what do you make bigger? Do you add more layers? Do you make the layers bigger? Like, the answer is you need to do all of that and also train on more data. And you need to figure out how exactly. So there is just one x-axis that says size, and the models are fairly good for this size, for this to work. And every training curve, like, it flattens at some point when you train too long. So it has this specific point where you've trained like just enough that training more doesn't pay off because you could just train a bigger model. And if you take these points and plot them in the log scale, then they form a very nice straight line, that, as you can see here. And that is amazing, because this tells you if you train an even bigger model, you know where it should be, right? It should be on this line. That's what you're predicting. And if it's not, if it's worse, then you know, like, oh, I probably have a bug. I need to do something differently. Maybe I have a bug in my code. Maybe I need to train a model in a different way. But you know that something went wrong, and that's extremely important, because if you don't know that something went wrong, you'll never get anywhere. So the scaling laws were amazing, because they also told us, yes, if we do this, if we train a bigger model, gather the money, make the GPUs work, then we'll get a loss that is of this size. And now, how does the loss translate to capabilities was less clear, and still isn't. But thanks to knowing where it should be, a model called GPT-3 was trained. And GPT-3 could, like, instead of just one paragraph like GPT-2, it could tell you like a whole story. Like, for example, you could tell it be a Dungeons and Dragons model, and it would talk to you, like, keep the story going. If there was some character, it would keep to it. So that was quite nice. But the thing that was more astounding is that it started doing things just by example. So previously, you had to train a model to translate from English to French. The results I was showing you before, you had a corpus of data. So there were researchers like us who went and made very sure that there is a data, English sentence, French sentence, English sentence, French sentence. This model has never seen a data like this, but you could tell it, hey, could you please translate English to French for me? And maybe for GPT-3, you have to give a few examples, and it would start translating. So this capability, which we call few-shot learning, or now, if you don't give any example, just describe what you want, it's called zero-shot learning. This is something that only exists for models that are trained with a lot of compute. So back then, the scale was measured with the number of parameters. Now we know that it's not just the number of parameters. It's how long you train, how good your data is. So nowadays, we have smaller models that can do that too. But it's something that clearly starts being good only when models get bigger. And when you have few-shot learning, then you start thinking, hey, maybe I can make just one model that will solve all tasks. So this is how we come to, to the current world, to our GPT-4 and ChatGPT years. So if you want the model to do what you want, then you need to take a step back first and think that the language models before, they were trained to just predict the next word. Just predicting the next word is not good if you want to chat with someone, because if you chat with someone, you're saying, hey, could you do this for me? And that is, you don't want it to predict the next word, which is, hey, maybe I could, and doing nothing, but you want it to actually do the thing. So you need to change the model a bit to follow instructions. The first data set is called instruction following. But also you may want it to, like, not be abusive, to not show information that's very controversial. to not swear, to like you may want to shape the model a bit to be better, which broadly we call alignment. So how can you take a language model and force it to be like this? Well, you collect some demonstration data from people first. So you say something and this is wrong, and there is a human that says this is wrong. So you actually gather data, and you gather data that is very specific. So you gather data, well, has it followed instructions? Was it like biased? Was it unsafe, what it's safe for children? Was it swearing? Was it you? So you specifically ask it to do bad things. You gather data. You also ask it to do just generic things and see what came out. And you get a lot of things like what would be a good answer. That's the first stage. Then you fine-tune the model on that and let it answer a bunch of questions. So you get like answers A, B, C, D. And then you ask people to rank them. Was A better than B? Was C better than D? Was C very bad? So they get 4 answers, and they score every answer, say from 1 to 6. And this data gives you what we call a reward model. So now when you have an answer, you train a model to predict how close is it to one of these. Is it good? Is it bad? Is it biased? When you have a reward model, you can now sample a lot of samples from your original model, because all of this data collection in step 1 and 2, there is only so many people you have. There are people you need to hire, they need to label data. So it's not like all of the internet. It's maybe a few thousand, maybe 20,000. It's not that many data examples. But when you train a model on them, then you can sample much more from your model. That's the RL part. So the first part is the human feedback part, because you get feedback from actual humans. And then you do RL on this reward model trained from this feedback, and train your model to make sure that you answer the way humans want, which means aligning with human feedback. And it turns out when you do that, it actually works very well, which you can see if you go to ChatGPT. So, something that when I started around 2013, 2014, people did not believe that you can make a neural network learn parsing when you had a data set especially for parsing, right? We had to write a paper to even show that you can generate a data set using existing parsers and then train a model to do this. Well, these days it's much easier. You just go to chat, ask it, do you know what constituency parsing is? And it doesn't predict just the next word. It gives you an answer to your question. It says, yes, I know. And then you can say, well, that's great. Could you give me an example? How would you parse John has a dog? John has a dog is the sentence that I had on the previous slide. And well, the model, the UI for some reason thinks it's C#, but it's not. It's just a bracketed form of a constituency tree. And it's a very correct constituency tree. So, and the model will even helpfully explain to you what all these things mean if you were interested. So that's quite a success. There is not a ton of constituency parsing data on the internet, right? This is not newspaper stuff. There is certainly some examples. So it's quite amazing that the model has learned from all of this internet data how to do this fairly narrow task. And not only can it do it, but it can follow the instructions you said and explain things to you. So you may say, okay, but maybe John has a dog is like a very basic sentence, and there was some guide to parsing on the internet. So maybe it had this sentence, right? Maybe it has just learned to do this narrow thing because that may be similar to like one of the websites that it has read on the internet. But again, similarly to the image generation thing, this is not the case. The model has really learned the rules because I just took, this was a sentence from the New York Times like some weeks ago. Could you show me the parse tree, no discussion for a sentence, renewed concern about the health of the banking system dragged down the stock market on Friday. It's like a sentence from, but it's a longer sentence, one that maybe it hasn't seen. And lo and behold, it gives you a parse tree that I think is fairly reasonable. But this model, it can not only do parsing, right? You can ask it, can you translate from English to Polish? And it says, sure, please. Here are the 2 paragraphs. And, it translates. It's maybe not the most amazing translation you can think of, but it's very correct. And this is like the GPT series of models was not trained with any translation data in particular. And it was trained on very little multilingual data. It was focused on English, right? I think there was maybe, not quite remember exactly, but probably around 10% of data was in other languages. So only from that, and without any specific data for translating, and just the instruction following also was not, it was just if someone tells you to do something, do it. It has learned to translate. It has learned to parse. I think it's actually probably better than Google Translate or on par. It can pass, it can pass a lot of exams that you can give to it. It's very much not perfect. So it's a dramatic change that happened in these 10 years. Now that you have these models, they don't need other training data very much. You can just ask them to do things. So okay, so if we have them, if that's also good, so what's left to do? Is this the end of deep learning? I don't think so. I think there is still a lot to be done and to be researched. And let me tell you, how I think about this and where this is going. So as I've shown you with these DALL-E examples, and now with the tasks that are not in the training data, but the model can do them, the key to a good model is generalization. So you're giving it data, and it has some examples of things, but you want the model to extract the essence of that, and with this to generalize to examples that it has never seen before. That's the most important thing. So how comes deep learning generalizes? Like where does this magic come from? And we don't have a fully scientific answers to that yet, but it seems like one important thing is this stochastic gradient descent. So with stochastic gradient descent, if you get a low loss on the training data, you usually also get low loss on the test data. Which is not guaranteed. You could make a tri-tree or do something else with your training data that's not backpropagation and no gradients, and you would get very low loss on the training set because you can just memorize it, and you would not get a low loss on the tests. So there is something specific to gradient descent that means that it's not just optimizing the train loss. It does it in a way that gives you things that generalize. So that's one ingredient. And when you do stochastic gradient descent, so you need an architecture of a network that's quite powerful, and you need to figure out how to train it well. So, for example, the recurrent neural networks that we started with, they were not that powerful, and they were not training as well as they should probably. So transformers helped with that. And I showed you the parsing paper. It was done on RNNs, but later we redid this with transformer in the transformer paper. And one thing that was astounding is that if you just take the small training set, which is 40,000 examples, the first line, then the results of a pure RNN without attention, the A, they're very bad. No matter how much you try, it will be under 70, which means what it generates is basically garbage. When you do this with transformer, you go almost as good as the handwritten parsers, only using these 40,000 examples. So you can tell that this network is much better by running only these very small experiments on the very small data set, because it shows you that it can use a small data already much better than the networks that came before. So if transformers are so much better than RNNs, then the question is, what can we do to transformers to get even better? Because transformers still have their limitations. They have only this many layers, and they can only do so many computations in that, and that's it. So people have been thinking about that for a while, and one answer that people at first wanted to use was recurrence in depth, because if you are recurrent and a transformer, then you can do more. But this has turned out to be quite hard to train. So the second answer that is very similar to recurrence in some sense, but it's trained in a different way, is to use what people call chains of thought these days. So what is a chain of thought? Imagine you are asking ChatGPT to solve a simple math exercise. Like your Roger has 5 tennis balls, he buys 2 more cans of balls, each can has 3 balls. How many balls does he have now? And you say the answer is 11, so that's one example. And then you give it another question like this, and then the model will try to just give you the answer. But the models, like, you sometimes can't compute the answer, like just give it out of the fly, right? There is some thinking you need to do, and the model has like no space to, it needs to do this thinking inside its layers, and that doesn't that may not be enough time and space to do it. So what you can do instead is, instead of immediately giving the answer, you can give a model an example of how would you think about it, so that every step of the thinking is much simpler than just giving the answer. So here you'd say Roger started with 5 balls, 2 cans of 3 balls. So there is 6 tennis balls in the cans, and he had 5, so together he had 11. And then the next time the model starts doing this, it will also think before answering. So this is the very powerful idea that you're not saying, model, answer me, give me the first token, second token, third token, and you need to do everything in your layers. But you can say, well, do the things in tokens. Like, tell me what you're thinking, and only then give the answer. And if you do that, there is a recent paper that says the model can basically do any computation. It can even execute programs. It's Turing complete. And does this really help? So on mathematics, you can see that you can tell the model, hey, do this thinking, but do it like number each step, like 1, 2, 3, 4, 5, 6, 7, as you see here, and be very precise about each step. And then you can try to verify each of these steps of thinking separately. You can even ask the model, well, was step 3 correct? Was step 4 correct? And when you do that, like this MATH dataset, which is a little bit tougher math problems than like the pure arithmetic, this was a dataset where GPT-2 could do nothing. It was especially made to show like what the models cannot do. If you add this thinking, you can get to like almost 80% just by allowing the model to think. And it's not just mathematics where you can build this thinking. So there is one paper of how GPT-4 can play Minecraft, and you can tell it to build libraries of functions of code. So as it wants to do something like get an axe, or it needs to do something in the game, it creates a code that is a routine that does something, and the next time it needs to do it, it can use this function it has created before. So not only do you have some thinking, you can access the thinking you did before, and here this is through using code. So people oftentimes ask these days, okay, so you can push these models to think, you can build libraries of knowledge, but will these models actually tell you the truth? Because oftentimes people say they hallucinate. So you ask a question, and the model that's just generating word by word, even if it does some thinking, it may tell you something that's not true. So a lot of people say, well, if you want the truth, you need to like have citations. Say somewhere on the internet it says something. So that's what some models these days have. So for example, I asked two versions of ChatGPT. What's the length of the highway between Aachen and Amsterdam? These are two cities in Europe. And you see the model that just hallucinates because it has only trained on the internet. It's clearly seen this somewhere on the internet because it says the approximate distance via the A2 highway is around 235 kilometers. But this is possibly a hallucination. The model has just trained on the internet and maybe it has seen this, maybe it hasn't. It's giving you some distance. So the other model, it has access to Bing. So it can create a query, send the query to a search engine, get an answer, and then tell you. So that's what the lower model did. It browsed Bing. It got the answer that the length is 229 kilometers or 142 miles, and it presented you the answer. So you may say, oh, the second model is more factual because it got it from somewhere. But I do not fully believe this because, in this case, both answers are correct. They're good answers. But the problem is what you find on the internet is not always true. And if you start asking more complicated questions, or maybe your Maps app is not good, you will get the wrong answer. And then it's very hard for the model to tell you something else because it has looked at, either it believes it or it doesn't. It's really hard for the model to judge the trustfulness of its sources, especially if you're training it to trust them. So people are like, what can we do to make these models be more true? And I don't know, but I think this is a very hard problem because to give you an example, the sentence, the Earth revolves around the sun, I think we all believe it to be true these days, but there was 1,000 years where people did not believe this to be true. There was a very famous book written about it that argued for hundreds of pages about why it's the Earth going around the sun and not the sun around the Earth. And a third of this book was totally wrong on top of this because it has the theory of tides that was wrong. So it is very hard to know what's true. And the models don't know it, but the internet also doesn't know it. And the only way the humanity has to get to what is true is to do a lot of thinking and to say, like, what would be the consequences of one thing? What would that mean? Can we observe that this is the case or not? And this is a very complicated thinking process that I think the chains of thought are doing like a tiny bit of starting to imitate it. But it's hard not just for language models, it's hard for humans too. And I think if you think what is coming in the next years, I think there'll be a lot of focus on doing this thinking thing with deep learning, with language models, probably with chains of thought, but also these chains of thought currently they're just prompted, but maybe you need to do some fine-tuning, some learning. There'll be a lot of work there, but this is a very hard problem to solve, and we'll start with much simpler exercises and probably move forward. But I think this is something that the coming years will see a lot of work. So that's what I had to say. And shall we go to questions? I can't hear you, sir.
Yeah, that's correct. Thank you, Lukasz. It was really the great presentations, and I see questions arise. But before that, I want to remind you that we are still independent as Ukraine due to our defenders, and I wanted to take another opportunity to remind you that to ask you to keep supporting them, and you can donate. You can make your donation by scanning the QR code or using the link in the description of the charitable organization's reactive post. And we'll go to the questions. So the first one arose when you were describing the RLHF process, and it sounds like there can be possibility that the labor itself is biased. So it's up to researchers to solve that problem. And how was it solved?
Yes, there is even the possibility that the researcher is biased. That is, that is what I wanted to allude in the end. We don't know what is biased. We don't know what is true. I mean, we know some things are clear, right? So we try to select for the things that are very clear and use this as a training data and throw away the rest and let the model do what it wants on the rest. But the notion of bias, even the notion of truth, has changed in the centuries. And it is not very clear. We don't have the answer. We certainly don't have the truth as AI researchers. So there is a big experiment now to try to make a democratic, like, have many institutions write like rules, and then people can debate every example and say, like, should the model do this, should the model do that. In many cases, maybe you don't want, like, maybe I can have my model that it's maybe more biased, maybe more cheeky and says some worse things because I don't care, and someone else will have a different model. So you can personalize the model. You can have a default that, like, many people debate and decide that this is okay. I think this is one reason why companies start engaging with politics these days, because in the end, it is the governments that have this task of deciding what's okay and what's not okay. But then the governments also don't do a great job always on that. So this is not this question goes way beyond AI. But since it's present in the language models now because they can answer so many questions. But how do we get to, like, an agreement together what should be done? And sometimes if it's like a physical question, how far is it to the sun? How do we measure it? How do we answer the questions for truth? But if it's a social question, how do we agree on something? That's a much bigger question. That it's AI, but it's not just AI, right? It touches on society and on a lot of other issues, how to agree. And I think these questions will be very important in the years to come. They go beyond what the models can do, but they also give great opportunities. If you have a community, if you have like a crypto chain or maybe just a community of people that can say, to, like, you only need to label this was okay, this was not okay. You don't need a lot of input from the people. You don't need to write correct examples. But if you have this input, then technically you can make the models follow it, and this could bring some good things or bad. But I think this will be a big thing in the years to come, where people can really make something new that uses the models, but goes much beyond where we are today.
Yeah, and you just at the same time answered the big AI alignment question. Like, how is it? Where should we go to possibly solve it? Because it's opened.
Yeah, we'll need to find ways to together decide where to go, and that's a hard problem. But that's also why I think it interacts with crypto, but not the money part of crypto, but so much as the distributed chain and responsive. Like, if you can track who said what and where do the things come from, then you can, because there may be people wanting to cheat, right? They want the model to think all the money should go to them. So you need to make sure that everyone votes just once, and you have all these kinds of problems. But we know how to solve some of them, at least. So I think there is a lot that will come in the years ahead.
Yeah, it sounds like the perfect startup for venture capitalists. The AI and ideas of blockchain combined. So yeah, to our listeners.
But
get
it
it
needs to
started.
start with the problem in mind, not with
Yeah.
how to get a lot of money from VC. That's
Yeah, and we'll go to the next question. So it's about model distillation. So as some of you know, when the model is trained, many of the weights are redundant. And what do you know about attempts to distill those large language models, and how did they end? How?
So yeah, especially recently, it started working a little better, I think. My understanding is that you can distill some capabilities of a large language model to a much smaller model. But if you want to have them all, then it's much harder. So, for example, you can distill alignment, which is nice. You can, if you want a model that's just good on math and code, then you can shrink the size by a fair bit. But if you want to have a model that's good at everything, then it's very hard to do that without the size, or at least I don't think anyone has managed it.
Great. And the next question, we will go to the base, to the foundation, to stochastic gradient descent. As you know, it's really difficult operation to calculate, and maybe you implemented some ideas, some alternatives to the good old stochastic gradient descent.
Yes, I mean, there were many things tried, but I think so far the good SGD with the Adam optimizer is still something we cannot beat. It's not that hard to calculate. It's good to learn. Automatic differentiation is very established now. There are good courses on it. It's definitely worth learning.
Great. Move to the next question. This one I want to elaborate myself. So the question is there any risk that we will face the data limitations in the future, data volume limitations? And my elaboration that there is this hypothesis that if it wasn't for the Whisper, which allowed to transcribe huge ton of English speech into text, we would not be able to create GPT-3 and further models. So it's like this combined question about the data. Do you see any limitation in the future? And is it true about Whisper that GPT-3 was based on the data set?
Whisper came after GPT-3. It was used for GPT-4 a little bit indeed. But it would have existed without it too. But it did benefit from more data. There is more data on the internet. You can scrape. There is way more websites than the current models use. But what you want is quality data. Like you don't want every, even for the big model, you don't want any website. So there is a lot of deduplication, but there is also, we throw away a lot of websites. And on the other hand, if you look at code data, so you have all of GitHub, there is maybe another bunch of code everywhere, but maybe you have 2 times GitHub. And that is only that's under 2 trillion tokens. So that's not a lot. I mean, GPT-4 was trained on 13 trillion tokens. I think that's public by now. So there is not that much code. And that's all the code on the internet. Like really, there's some private code at Google, but we're out of code. And if you go especially to mathematics, to things like parsing, there is not, some domains just don't have the data. So that's why I think generalization is the key to deep learning. You really need models that can work. They can work with a lot of data, but they can work with a little data too. And transformers are not that bad. You just need to tune them a little differently. They can work with like 50,000 examples, which is not that little. But if you make the models more powerful, like for example, if you use chains of thought, the models become more data efficient. So they can learn from fewer examples. We don't yet maybe know how to, because with chains of thought, there is like you prompt, it's just like, it becomes more, like it's not just pure train it. It's a more involved process because there is this something that's generated in the middle. But I do believe that this process will allow us to do models that are very data efficient, and that will help with the data problem.
Yeah, and perfect. Next question. As we're speaking about more general models, it's multimodality. Do you think this is the answer for reasoning? yeah, as reasoning is really good in GPT-4, but many people claim it's not as good as it's not production level good.
I I think multimodality is great and important. It will add a lot of data. It will help with some forms of reasoning, like physical reason, like what will happen to a nail when you leave it in the air, and things like this. I don't think it is exactly the answer. I think for reasoning you also need these chains of thought that like you need to give the model the ability to think longer than it has layers.
Mhm.
And but it can be combined with multimodal, especially when you have like nowadays models, they can like generate, you say, okay, how does it look when a boy kicks a ball, and you can generate a few frames of the video, and now more and more there are models that will generate the whole video. And then there start to be models of the world that say, well, if you drive a car like this, how will the street look, how will the people look, what will happen, will you crash into something? So in the future the models will have this knowledge of the world and this generation, which we call chain of thought in text. But multimodality, this means just it's a chain of frames of what's going to happen to the world, which is basically how we sometimes think. What will, if I go somewhere, what will happen to me? And I think that will indeed be so it will be multimodality and this ability to generate sequences of things before you give an answer that will resemble much more what we call reasoning. But you also need to learn how to train it, and that's not yet solved.
Yeah, great answer. Thank you. And the next one is about Llama, is about open source version of open source LLMs, and it's so Llama can perform in metrics as good as GPT 3.5, but their answers are not as good. So, how many tricks beyond those LLMs does ChatGPT use?
I think ChatGPT uses surprisingly few tricks. It's actually, we always laugh that if we tried to publish a paper, it would be rejected because there would be nothing new in it. There is a lot in doing the basics right. I mean, right means, when you train a model, there is a lot to optimize. It's a lot of work to make sure you don't have bugs. That's why you have the scaling clause. I mean, I draw like one line, but in fact, you'd never know where the line is. There was a chinchilla paper that improved. We have now even improved. So you need to make a very careful fit. You need to check very carefully if you're training well. Adam has like 3 parameters, beta 1, beta 2, and an epsilon. You really need to understand, should they change? Should there be a schedule to them? Is it related to your learning rate schedule? Do you need weight decay? All of these things. And then when you do RL, you have all of these questions applied to PPO, like how do you tune it really well? And you need to start studying it on smaller models and see how this changes with size. So it's a whole science of how to optimize both normal supervised training and RL, and there's just it's like a science of making a plane. You need to optimize the aerodynamics of your model very well, but there is nothing of like a big tricks or ideas to this. It's just studying very carefully how you change the parameters, what happens with size, and then you see what happens, and then you pick the best, and that helps you get better models even when they're smaller. So.
Yeah, and as we're speaking about open source LLMs, the question is, what do you think about them in general, and which role they can play in the future?
I like open source LLMs very much. I have very high hopes that OpenAI will open source some LLMs in the near future. There may be more about it on November 6th. We'll see.
Yeah, we'll look forward to it.
There are like I don't think it's like you can't open source GPT-4, and not just because it could be dangerous, even though I'm not sure GPT-4 would be dangerous, but the models that will come may one day indeed be. That's one argument. but because you would not be able to run it. Like it's very tied to a very specific hardware configuration, and it would run so slow for that it would be useless. So it doesn't make sense to open source exactly this model, but there will be models that will be open sourced that will be similarly powerful. Well, maybe first they'll be a little less powerful, but I mean, already we have models that are more powerful than GPT-3 that are open sourced, and there'll be more powerful models coming next year, and they'll be maybe tuned to, maybe you want to run a language model on your phone. Maybe sometimes you don't have a network. If you want to run the biggest language model in the world, you probably will need a data center. So you like you don't want these models weights. So yeah, this is a balance, but I think it's nice that there is a balance. Like there should definitely be open source models. Whether the biggest one should be open source is a more trick. Maybe maybe it should get open source like half a year later every time, or that's like I would be a little scared if it got open sourced immediately every time. but yeah, there is a lot of debate around it, and I mean, open source is here. It was always there, and it will be there. And the question is how to make it so that it's both usable and doesn't have like any weird results.
Yeah, and I myself want to elaborate this question. So there are two narratives that are being speculated about the future of AI, whether it's going to be as one big model like GPT-4, or it's going to be in domain-specific, more smaller models. In which future do you bet on?
Oh, I think they're both be true. I think there'll be. I mean, currently we don't have a way to make small models be as generally good at everything as big models. So if this continues to be the case, then you'll still want one model that can just do everything. But if you work in a specific domain, like you want a model to do your taxes, you don't care that the model writes poems or can do rap lyrics or can do chemistry. You don't need this. But you want to run this model 100,000 times a day for a lot of tokens. Then you will want to distill it because it will just be cheaper. And of course, then this will be a smaller model. So I do think that there will be areas where you'll want a smaller model, but then there will be areas, you want your homework in something. Maybe it's not worth distilling a model for second grade homeworks. So you'll just have this one model that does like the long tail of all other tasks. But we'll see. I mean, deep learning has always brought surprises to me too and to everyone. So I'm sure it will still be interesting and surprising.
Yeah, likewise. Another question. So there were lots of experiments of fine-tuning existing open source models on synthetic datasets generated from GPT-4. What do you think about such approach? And can LLMs improve using LLM-generated text?
Well, so I certainly hope so, right? I mean, we do generate some data, and if you manage to filter out for nice data and it's varied, then it can work to some extent. But there are also recent papers that if you generate, then everything collapses into like the models use less and less vocabulary, and they start to do weird artifacts, and everything goes wrong. So I have. Yeah, I mean, chains of thought are an LLM-generated data, and I think they're key to in the future to making the models better. But it's not that simple that you can just generate and train on it, and that's it. You need to generate, but have like an anchor to reality, to some other text or to something. and you need to be careful to not collapse, like not have mode collapse. So I think there is something to it, but we haven't yet figured out. Like there were very recent papers that show, like, start investigating why things collapse. I don't think we have a recipe to stop this yet. That would be great. That would solve all our data problems. But I don't think we know how to do it yet. But I think that it can be done in some ways. It's just
Mhm.
more
Great.
research.
Lots of different questions. I'm sorry for not picking all of them. I'm trying to pick the most interesting one. The next one is about AutoGPT. What do you think about such approaches and tooling for LLMs in general?
So I'm not sure I have full knowledge which one is AutoGPT.
It's like this approach of AI agents, like AutoGPT, Baby AGI. The thing that is like in while loop, it decomposes each high-level assignment into subtasks, and it knows which tools to use for each of them. And yeah, it's like based on React paper.
So I think that's very interesting. I believe so this is almost like a chain of thought, but it has other agents that speak. I think there is something in this approach that is very interesting. It feels like there is also something missing yet. Like, in the end, when you do all of these interactions, there is something that comes at the end, and there should be some way of training, like, oh, it worked, so this was good. But what was, like, it's a sparse reward kind of problem. We know how to handle them to some extent, but I don't think this is yet, like, I think for now it's just prompted, and the model does things and comes up with something which is good. Sometimes it comes up with better things than in one step, but it's a little bit like just the prompted chains of thought. It would be nice if you could train them, like make the model improve these things in some way. And I don't think that's yet figured out. But it's all of this is very new, right? It's very hard to even with GPT 3.5, it's very hard to do this agent things. Well, with GPT-4, they start to work. So it's like on the very edge of our abilities right now. And then maybe we simply need one more bigger model and better API and like. Yeah, I think there is a good future in there. It's just very new and not yet researched enough to.
And continuing this topic, how do you think about AI assistants in the future? So it's like ecosystem that is combination of different kind of tools, and you're certainly moving in that direction, not only with GPT Daily, but with browsing mode, with plugins, data analytics mode. Yeah, what are your thoughts? Maybe some tips?
So yeah, it's tricky situation. There is an event next Tuesday.
I got it, yeah.
And I shouldn't like. I think you should tune in. Like I shouldn't say too much, but there is definitely, there is a lot happening in this way. We have a dev day on the coming Tuesday, and there'll be definitely much more about that then. And I feel like I shouldn't.
Yeah, thank you for not spoiling us.
I feel like
and we are happy that it's just 4 days left. Otherwise, yeah, we would be really pushing. Next question. Like, aside of all of the technical stuff about researching new approaches, which skills do you think we need to develop to make sure we use those future models in the most efficient ways, like on everyday context, not as researchers?
That's a hard one. I ask this myself a lot. I feel like I use ChatGPT not the right way. Like I copy paste, I kind of ask it, then I give up. Like how to work with these AI things at your side. I think it's harder in some sense than making them, because it's like a new thing. It's not easy to switch to it, and they'll be changing. I think it will take a while to figure out. Like, Microsoft puts co-pilots in everything. Google, like, now everyone wants you to have a chat on the site. So you chat with the website, chat with your dog, chat with the make me this slide. I've never managed to convince myself to work this way yet, but maybe we will, right? Maybe it will be voice. Maybe you'll just talk to your thing and it will. But I feel very weird talking to my screen in the office, But but I feel like it's almost like asking, sitting at an Atari computer and asking how will we do video calls. We don't know, and it will take a while to figure this out.
Mm-hmm.
It will be quite curious, I think. But I struggle with this.
Yeah, what a time to be alive, as in 2 Minutes Paper said.
But it's interesting.
Yeah, it does. Back to the technical questions. So, what do you think about GNNs in NLP, like generalization of transformers?
So I think GNNs are very interesting. I feel like they're more suited for more like chemistry and like in NLP, it's it's I don't think they have been like, they're a little slower, right? So you get some improvement, you get some speed penalty, and the trade-off has not been there so far to I mean, transformers are just optimized and simple, and the GNs have not been like, there's many networks that are a bit better, but just the betterness is not worth the trade-off.
Mm-hmm.
I still think they're very interesting. I also, as I said, I always found recurrent architectures interesting too. But in the end, like recently I do chains of thought because like infrastructurally, you can just sample from transformers. There are libraries for it. They're very optimized. You can do this, and the sampling, like I feel a lot of these methods you could use one or the other. It's a lot of the issue is like, what do you have good infrastructure for? And but we should keep trying. Transformers are not the end, right? They're and you can do chains of thought to extend them. You can do GNNs, you can do recurrence in depth. We should do a lot of, they're like these models like S4, S5. They're very interesting. RWKVs. We should keep trying. There is you only find things when you try them out.
And the next question. So ChatGPT is basically created, in my opinion, the new type of the job. And to that new type of the job, the question, what do you think will happen with NLP, machine learning engineers and researchers in smaller companies? Will they be replaced with like prompting plus using OpenAI API or other LLM?
Yeah, I don't. Well, I mean, I know some programmers at some companies got replaced by LLMs, but I think that is very rare still. I think that, I mean, I use language models. I ask it for code. I switch to Visual Studio to have the Copilot. So a lot of my code is written by an LLM. Mm-hmm. Nobody is replacing me because of that, and I think this applies to a lot of engineering. Like, I don't think the models are close yet to like fully replacing a job. They're assisting, which maybe means there can be fewer people doing my job, but like in software engineering, there's always enough to do. We still have so many bugs everywhere that I wouldn't worry that much in the short term. And in the long term, it's very hard to say, well, where is it going to go. So I don't think that the LLMs are. I think for smaller companies, the issue is usually, do you have a solid business case? That as it has always been. And I think if you have a solid business, then you'll keep your engineers because they add value. And it's also, there is a lot in like going to people and asking what they actually want from whatever you're doing, right? And language models can't do that for you. And it may be, there's a very human thing to this. So it, like, they may help gathering data or like, things, but I still think, in the end, business is what humans do to humans, and it may, maybe you'll need to talk differently to people, or like the kind of work we do may change. Like it may become higher level, right? We may just go and talk about what are the requirements, what would people want to have, and then the models will do more of the boilerplate things. But I don't think, there's just so much more that people would want if you could offer them to do it, that I think software engineering is not close to losing jobs. But again,
yeah, who knows? Another one is not the question, it's idea that I want to transform into the question. So it's like idea to block GPT from answering certain questions for a couple of days to students, because even the trends show that one of the biggest audience of usage of ChatGPT is students. And I heard that OpenAI is on a track to create this, not trademark, I forgot it, watermark, which will allow to detect whether the text was generated with ChatGPT or not. So the question is, can you update us on that track? Do you think, is it possible at all to create such a system? And if does, like one thing for OpenAI to create it, as you know, all of the internals of the model and how you generate them. And another thing, like for third-party providers to do that. Yeah, so to wrap it up.
So there are two sides to this question. One is like, is it technically possible to generate text that is correct and sounding like a language but has a watermark? And the answer is yes. You can read Scott Aronson's blog to see the exact details, but you can just, like, in the frequencies of words, you can like manipulate them so that it will be recognizable statistically from a bit longer text that it was. Well, then you can like put, if it gets rephrased, it can be broken, right? But there is a lot of watermarking that can be done, and so technically, on the scientific basis, it's an interesting question, and the answer is mostly yes. So you can watermark text to be recognizable. Now then, if this text changes, it may stop to be recognizable, and there are changes like, for example, you can generate a watermark text with ChatGPT and ask Llama 2 to rephrase it. Now the Llama is not watermarked, it will generate you text that doesn't have the statistics, and it will probably break or you can simply ask Llama to generate the text in the first place. And it's not just Llama, like the point is, it's just, we assume we're in a fairly open society and we have open models, and we want this openness. We don't want everything, we don't want OpenAI to dictate the rules. We don't want anyone to like very much dictate the rules. On the other hand, of course, we don't talk about, like, that's why we have human feedback and alignment. There are certain things we really don't want, but everything else we kind of want to at least have the possibilities. So the high schoolers are usually the smartest people around. So if ChatGPT blocks them, they'll find the other model. it's not the fight you want to fight, right? So on the one hand, yes, it's possible to a large extent. On the other hand, well, I saw a lot of homeworks that already say as a language model. So for the students who are so lazy, it's easy to detect. You don't need to watermark it. For the ones who are smart, they'll find their way around, and also they should probably start learning how to use this more in a better way. So it's a tricky thing, but I don't think, I generally don't think blocking. I mean, you need to block, weapons. There are things you need to block, right? You don't want some kinds of stuff you don't want out, but the rest, yeah, it's blocking is probably not the best way. But on the other hand, I think teachers will manage. There's a lot of fun things you can ask the students to use the models for, and in the end, I remember my PhD supervisor. So these days, I think when you do a PhD, you need to go to a lot of courses. When I was doing a PhD, I was teaching courses. I didn't have to pass any exams except for the final one. And my PhD supervisor said, well, when I was doing masters, I was just walking around the university talking to professors, and my final exam was to talk for 2 hours to someone and convince them I've learned. So maybe we're going back to the way it was. Like in the end, we shouldn't grade students on how can they write 1 page, 2 page every 2 days. There's too much, if you think 50 years ago, the education did not have this overwhelming amount of homeworks, but people had to talk to other people like live to be graded. And they were like, well, no, you don't understand. And that was the grade. So we need to go back to that, but maybe for the better.
Yeah, it was a great comment that students must learn prompting techniques because, chain of thought would not allow spoiling the text with act as a language model and provide an answer.
Yes, but even if it can in the next version, hopefully, yeah, I think the final exam should be the teacher talking to the student without any intermediary, live, not virtually, and that's a fairly good.
Perfect. Yeah, great. We've got 2 questions to go. So the next one is we spoke about stochastic gradient descent, and the next one is about non-gradient optimization methods like genetic algorithms and sworn algorithms. What's your opinion on them? And
I think they're very interesting. I think they're especially in the context of RLHF, right? We do RL, we do PPO for now, but it doesn't like this human feed. This is not RL like the Walker, right? It's not like Atari games. There is none of this interaction. So there is like a DPO, the direct preference optimization, and it seems like much simpler methods could be used there. On the other hand, like RL it's not a gradient. I mean, there's gradients in some steps, but it's not a gradient method. So especially if you want to do like very long answers, right? One advantage of the ES and evolutionary strategies is that it doesn't depend how long your answer is, right? You can speak for thousands of words, and there's just a 0 or 1 at the end, and use that to optimize. So I think it's very interesting to use them there. That's a use in RL. So they're not necessarily replacing gradient descent. There is the other track of work where people try to do like no gradient descent. There's like forward from Jeff Hinton, and I think that's very interesting. But on the practical side, it still seems far from the performance you get just from SGT. So I think like the on the practical side, the most interesting thing for these no gradient methods is the RL side.
And at this moment we've got two more questions. I'm sorry, it's like people
Sure,
already.
no worries.
Yes, so the next one is, how do you see the next 2 years of deep learning?
Yeah, I think they'll be as interesting as any previous 2 years or even more. I think there'll be a lot on the chain of thought, but very generally speaking. So also on the agents, building libraries of knowledge, possibly multimodal, where the chain of thought is basically a simulation of the world. So I think that will be like one big topic, and I think this will make the models generalize much better from less data too. So that will be a big boost to a lot of like also more specialized things. And on the other hand, there is this question: what do we want to align to? How do we decide that something's true and not a hallucination? And I think there is a big role for the community there. And this also, like, if you do this, then you'll have agents that do like a lot of sampling for, if you have this agent architecture, sometimes there's like, summarize me this web page or something like that. So there are tasks that involve a lot of tokens that you need to do a lot. So you need smaller models to do this. You can't ask your biggest model to do all of that. So there'll be much more of like, can you have a smaller model that does a more specific task, like maybe just summarize or just browse, or maybe it needs to be a bit general, but it doesn't need to be so good. Yeah, so I think that'll be interesting, because some of these models can be open, some may not be open, they may interact. There may be even like some economy like thing that you pay for a little of tokens of that, but do some works with the free model. Like, but on top of that, the big question will be like, can we have a community way of deciding what the model should do? Can we like propagate that? If there is like a really large community, thousands of people, hundreds of thousands, thinking about something, can we propagate this information into a model? And that's where we don't really know how to do it yet, but I think we'll need to, because we don't want, like, OpenAI does not want to decide what your model does. That should be decided by people in the big picture, but it's hard to ask the politicians to decide this. It needs to like have a different way. So maybe some chain methods, maybe we'll see. I think there will be a lot though. So there are like these two big things that I think will.
Yeah, and another questions. Another question about the future, and it's gonna be the last one for today. Sam Altman said something like, intelligence won't be that valuable soon. So what are your takes on that?
Well, I don't know. I don't know in which context Sam was thinking this, but I think the context he has in mind usually when he says things like that is that there was a time when people thought maybe AI will replace like simple jobs first. Maybe it will replace drivers, right? And in San Francisco, there are self-driving cars that are fairly good, but it does feel now that it will take years for them to really drive like everywhere. Like drivers seem pretty safe for the next good few years. On the other hand, if you're doing something like writing statistics or like some low-level data analysis for some company, like there may be a model that will do a large part of your job. I don't think it will do, like, if your job involves asking people what they actually mean with their question, that doesn't do that yet. But maybe you'll need way less people doing that, because some Excel things used to be very hard, and you need someone who's especially learned that. While now you can just ask. So in that context, I think it will like valuable in the sense people will pay less for some sort of skills, because you'll be able to just ask chat to do that. But maybe we'll decide that these were skills that we didn't like very much anyway. Like, I've been doing this kind of work sometimes before, and now that I think of it, it wasn't that great. So, but yes, there'll be like there'll be some skills that will be less valued because they'll be done, and there'll be, I think, human skills and a lot of other skills that now will have more recognition, hopefully. So,
yeah, and and I guess we're wrapping up on that. Honestly, Lucas, it was one of the best sessions of my life personally. I don't know what about other
thank you very much. Thank you for the
participants.
invitation. It was great
Yeah,
to see you. And
yeah,
Slava Ukraini.
yeah. Heroям slava. Thank you so much. And
Bye.
yeah, all of the participants, feel free to leave grateful notes for Lucas for this session. And another thing I wanted to add is just to thank everyone for coming and for listening and for asking such great questions. And want to remind you that this lecture, it is recorded, it will be available, and they will be available on the AI House website, which is on the link under the video. And we'll be grateful for you to share the information about our project, as your support means really a lot. And Lucas, thank you
Thank
one
you
again.
very much.
Yeah, it was awesome. Thank you so much.
Bye.